Okay. Yeah, we also talked about Tron. We found out mostly about it. It has a high transaction throughput. It focused on entertainment and content distribution. We also talked about Ripple. Ripple is a decentralized platform that allows digital and fiat currencies to be transferred across international borders. We also we talked about Avalanche, which was a private permission blockchain network. And yeah, that's pretty much what we did.
Thank you so much, Samuel. That was very good. Yeah, so that was very, very good. Like, that's a very good thing to share. So I think on top of what you've done, it also be
All right,
great
we
if
also
you
have
could
a
also share it.
presentation.
All right, Samson. Okay, just a bit.
Okay, this is from group one.
Okay.
We also have a presentation that we did. So I'll just share my screen.
All right.
Okay. Coming. Okay, I'm doing that already. All right, so this is our slide. This is our slide. So basically, the person that's supposed to represent us is not available. All right, he's not feeling too well. So we just have to run through this. So we looked at an overview of different blockchain network, which the first one is the public blockchain network. Then we have hybrid blockchain network. We have the private blockchain network and consortium blockchain network. All right, so moving on to the slide 2, we actually looked at we broke down the public blockchain network. We looked at the advantages, we looked at the disadvantages, and the uses of it. So we come to discover that the public blockchain network is a permissionless network that is not restrictive, right? It is not restrictive, which simply means that the users can access current and past record, conduct mining activities, right? So like it is said, like for example, the Bitcoin can be seen as one of the public blockchain network.
Sorry,
right?
excuse me. Hello.
Yeah.
Sorry, can you hear me? I don't know if it is your phone that is actually ringing, so it's disrupting what you're actually saying. We can't hear you loud and clear because something is ringing. I think it has stopped now.
You can proceed. Just make sure you make your presentation a bit faster.
Please, after this, I also have a presentation in place of my team.
Yeah, so Samson, we need to proceed. You mute. Samson, you mute. So just present what you have, then you can proceed to the next person.
Yes. Let's proceed.
Okay.
Let's proceed. Right.
Page 18 and 19.
Okay, I'm good.
The language here is 72B. 72B. Huh? When they are talking, you not listen.
Samson, you can proceed. Or you're finished?
Oh, did you say I should proceed? I thought you said we don't have much time.
Yeah, like you finished presenting.
Okay. So that's for what's it called? I'm sorry, I've actually closed my all right, I think we should just proceed. I think I actually closed my this thing. Well, can
No
you see
problem.
my screen? Can you see
Without
You can see the screen, yes.
You can see my screen. Okay, okay,
Yes.
okay. So we moved on to what's it called? The second one, which is private blockchain. So we said the private blockchain is a network that works under the control of a single entity. That is, it can be controlled, right? It is restricted. It is not totally accessible, and this kind of blockchain network is being made use of by the banks, right? Like banks, for example, make use of this kind of network. It is not everybody that can access their system. It has to be authorized, right? It has to be authorized. Then one of the advantage is the controlling organization set permission level, security, authorization, and accessibility. One of the disadvantage of the private blockchain network is that it includes controversial claim that they aren't true blockchains. Since the core philosophy of blockchain is decentralized, it's also more difficult to fully achieve trust in the information. It's just like I'm banking with a particular local bank. Now you can actually trust them to an extent because we have heard of different banks that fold up and all of that. And also we have different blockchain platforms like that also, that actually you invest your money in it, and at the end of the day, maybe for like 2, 3, 4, 5 weeks, and you just hear that they have shut down, they have closed down, all your asset is gone and all of that. So one of the and also we found out something called use cases, right? We said this the speed of private blockchain makes them ideal for cases. Now, this is actually talking about the transaction process, the speed of transaction. In the public, what's it called? In the public blockchain network, the speed of transaction is more smooth because of the population of people that are actually into it. While in the private network, it is not, what's it called? The speed is faster. The speed is faster. And also we looked at
So,
hybrid.
Samuel, you may need to
Yeah, I'm
shorten
with
up.
you.
You have 1 more minute.
Okay. Wow. So we look at the hybrid, the same thing. We look at the advantages, disadvantages, and the use cases, and also for the what's it called? Consortium blockchain. So that was all that we did research about. And also but we didn't put it down. We did research for what's it called? We did research for transaction, what's it called? Input and output transaction processes.
All right, great. Thank you so much for that.
Yeah, thank you.
Thank you very much. So I think you can stop sharing. Then I think we can have is it Unity last.
Okay.
Ah,
Yeah.
my group.
okay. Here, can everyone hear me?
Hello. Yes.
Yes, we
Okay,
can hear
let me
you.
share my screen.
You can stop sharing, Samson.
Samson, please stop sharing so that I can share my.
This guy should take off his own now so that we can share our own. Yes. I think there's no group two because there was no one inside group two. Okay.
I think okay, you are unmuted. Can you just mute, please?
Okay, let me share my. Okay, can you see my screen? Hello.
Yeah,
Yes.
Okay, so we did the comparative analysis of Ethereum as a blockchain network. That's what I and my team talked about last night and related to this morning. So this has most the things we talked about the history of the Ethereum blockchain, and we were able to understand the introduction and the early development of this blockchain, where the founders were founded by Vitalik Buterin, and their vision was aimed to extend blockchain capabilities beyond Bitcoin and focusing on smart contracts, decentralized apps, and NFTs. Then we were also able to cover the white paper on crowd sale, which started between 2013 to 2014. And it was introduced in 2013, where the Ethereum white paper outlined the vision. A successful crowd sale in 2014 raised over $2 million, making it a groundbreaking ICO. So see that this Ethereum blockchain, their aim here was really, really strong enough to since Bitcoin was the only like the outstanding network then, Ethereum came up so that it don't they also do something like that, but also have a wider range of it. Then we talked about the milestones and the upgrades. The network launch, which started between 2015. The Ethereum's live network Frontier launched in 2015, which enables developers to build decentralized apps. And we still have that still today. Then we talked about the upgrades and challenges, the transition to proof of stake, and also the DeFi and NFT boom. Uh, those things has really helped a lot of blockchain developers today. Then we also have the Ethereum consensus mechanism, where they have the proof of work. This proof of work, Ethereum initially used proof of work as a consensus mechanism, similarly to Bitcoin, requiring extensive computational power. But right now, they are not using the proof of stake, where it started in September 2022, where Ethereum adopted proof of stake as its new consensus mechanism. Why is that? Because the shift to proof of stake dramatically reduced energy consumption by 99.98%, according to MDPI.com, making Ethereum more environmentally friendly. So we see that these people, their mission was really to make things really easier for transaction's sake. So the Ethereum security and cryptography, its early security focus was security foundations. Ethereum inception included a strong focus on security, building on the lessons learned from Bitcoin. Then the ongoing enhancement of cryptography, so that how they were improving as the year goes by from 2016, 2017, 2019 to where they are today. And today we have the smart contracts, where Ethereum introduced the smart contract of self-executing contracts with coded terms, enabling automated and trustless transaction. You don't have to get a third party before you can do your transactions. And the vision of the white paper that was also embarked in 2013. The evolution and the impacts. The famous DAO incident exposed vulnerabilities in smart contracts, leading to a hard fork and the creation of the Ethereum and Ethereum Classic, and the ongoing developments. Despite the challenges that Ethereum continued to enhance and optimize smart contracts through various upgrades like Metropolis in 2017-2019. So the Ethereum scalability solutions is that, first of all, it's transition from proof of work to proof of stake and
Hello.
implemented. Yeah.
Yeah, you got a minute left, so please wind up.
Okay. Let me go to. Okay. The reason why I like Ethereum is this mechanism on the models in which they govern. Why? Because Ethereum improvement proposals, one is primary governance forms submitted by community members for changes or additions to the Ethereum protocol, either a proposals or undergo rigorous review or ensuring transparency and inclusivity. So what is the governance tokens? It projects in the Ethereum ecosystem, issue governance tokens, granting holders the right to participate in decision making. And these tokens enable community members to vote on proposals and shape the project's direction. So these are some of the things I and my team worked on last night and so this morning.
All right, thank you so much for that, Trinity. And I'm very sure everyone was thank you so much for doing your assignments. So ideally, there's a Google form that will be sent to the group. So kindly be sure to submit your assignments there. And also be sure to share your work with the rest of the team. So at least we can able to share information within the class. Okay. Great. Great. So think we can, without further ado, we can start with today's content. So allow me to share my screen. So can you see my screen?
We can see your screen, so.
Perfect. Okay, so we can start. So cryptography. I think you must have seen this word being thrown around yesterday during this class a lot.
Yes,
And
very
so
well.
today's, I think you can just, I don't know who's talking, but you can just mute. So today's class will be focusing a lot on this cryptography. We'll be looking at ideally what you need to know as a Web3 engineer, the basics really. We'll ideally go in depth because the basis of cryptography is basically maths. So we'll just be looking at it from the top view, trying to understand different terminologies that are essential for you to get started and be able to build smart contracts without any issue. So I think before we can start, can someone tell me what they think cryptography is all about? Can you just type in the chat? Let's all meet and type in the chat. What do you think cryptography is all about? Albert Owusu Jashie, I think you need to mute. Same thing to Deborah, Jacob, and Wisdom. Kindly mute. So what do you think cryptography is about? Why do we need to learn about cryptography? So what is it really? Coding information so that the only person message was intended for can read it. Okay. Okay. Encoding data. All right. Encrypting information so that only the internet party can understand it. Okay. Privacy of data, encryption. Wisdom, kindly mute. Cryptography is coding a message in that only the receiver can understand the message. Okay. Study of secure communication techniques, right? Security. Well, okay. It is a practice and study of techniques for secure communication in the presence of third parties. Okay. Okay. One-way hashing, end-to-end encryption. Okay, so from the chat, I can tell that you have an idea of what cryptography is, which is great. Right, thank you so much for your participation. So, well, cryptography, as some of you have stated, is a practice and study of techniques to secure communication in the presence of adversarial behavior. So, ideally, an adversary is basically someone trying to access something they're not meant to access, basically. So that's an adversarial behavior is that act of this particular person trying to access something they're not meant to access. And that's really just what cryptography is all about, the art of trying to make sure that communication is secure. Okay. So when talking about cryptography, the basis or the sort of like the underlying building blocks of cryptography is shown in this particular image right here. So we have two entities, as you can see, we have a sender and a receiver, and P stands for plain text. Okay. And E stands for E stands for the encryption process, and C is the ciphertext. So ideally, if the sender wants to send something to the receiver, and let's say they want to send a text hello world, right? Want to send the text hello world. Ideally, what will happen is they would encrypt the plain text using a key, and the key produces something we call a ciphertext. Okay, so the ciphertext is basically not anything that a human can understand. It's basically, it's sort of like, to you to look like jargon. And once this particular piece of information is ready to be transmitted, basically transmitted through a channel. So the channel could be anything, could be through the internet, could be via a piece of paper, really just any time to get to the receiver. And once it reaches the receiver's point of view, we use another key to decrypt. We can use the same key. We can use the same key to decrypt, or in some other cases, we might end up using another key to decrypt that particular piece of ciphertext and now get the actual plain text. And you can see within this case, cryptography basically is this
Sorry,
process of
Mr.
making
Victor.
sure that.
Mr. Victor, sorry. There's
Yes.
some. I think you should mute everybody. There's somebody talking by the background.
The host, can you just mute everyone, please? Thank you for that. Yeah. So, Blessed Kevo, you may need to mute, please. Blessed Kevo, can you mute? Right. The host can you mute Kevin. Yeah, so that's basically much about cryptography. Okay. So, we'll be looking at cryptographic primitives. So basically, what do you mean by cryptographic primitives? A cryptographic primitive ideally is think of a cryptographic primitive as building blocks of basically like a little like the building blocks of an algorithm designed to secure the communication of that information. I don't know, host, can you
tell Blessed to mute?
I am actually muting them on my end. I don't know what's happening. So
okay.
just please continue. I'll keep muting them. So sorry about the interruption.
It's okay. So yeah, as I said, a cryptographic primitive basically represents the low level algorithms that are used to design these secure algorithms for communication. So ideally, much of your work as a Web3 engineer will be trying to play around with these primitives to make sure that whatever you're working on is always going to be secure. All right, thank you for that, Francis. So I think we can get started with hash functions. So again in the chat, so what do you think a hash function is? I think I already talked about it yesterday, but if you remember, please type it in the chat. What is a hash function? What is a hash function? Warren Kanga, please mute. Thank you. What is a hash function? People kindly type in the chat. What is a hash function? It's a one-way function that keeps data. Okay, all right. Thank you for that, Mr. Grades. Math function that alters data to strings. A math function that converts data into a string with a set amount of characters. It is used to map data to a fixed size. Okay, thank you for that, Unity. Thank you for that, Ipiana. Thank you for that, Wycliffe. Thank you for that, Agbo. So yeah, I can see you have an idea what a hash function is. So, as you just said in the chat, a hash function is ideally a mathematical function that converts an input of any length to a binary sequence of a fixed length. And it's good to note that actually hashing is not encryption, okay? So why is that the case? The idea behind encryption is that whatever you're transforming should be able to be transformed back into the original message. But in terms of hashing, once it's gone, once it's been transformed, it's already transformed. You cannot work back to it. And that's the reason why we have that explanation down there. So it's a hash function is a versatile one-way cryptographic algorithm that maps an input of any size to a unique output of a fixed length of bits. So what does that basically mean? It means that no matter how long a message is, if the result of the hash function has to be 10 letters, it will always be 10 letters, no matter whether you write a 10-page composition, whether you end up writing just a one-letter word, it will always be 10. It will always be 10 characters long. Okay. And so the resulting output will always be, could be called a hash digest, hash value, or hash code, and it's always unique. Okay. So remember, hashing is not a good thing to note is that hashing is not encryption. So there's a video right there that you'll be that you can once you get the notes you can go watch. It's a video by I think for those who know computer file, it's a video by computer file. One of the engineers talks about ideally hashing as an algorithm. So kindly, once you get the notes, be sure to watch this particular video. It's very much essential for you as an engineer to watch this video. So yeah, one-way functions, ideally, a one-way function is a function in which the resulting output cannot work behind, you cannot basically move from there. You cannot really work the results from the right side to the left side. So once you hash the data, ideally it doesn't matter like what do you call it? It's not in sort of way like a noble encryption sequence. So you hash where you can transform the data and you can basically work back to the original data. Once it's hashed, it's gone. Okay. So if you don't have the original piece of data, you cannot be able to create the hash again. So ideally, why do we use hashing? What is the need for using a hash function? As you can see from that piece of text there, is that trying to brute force the result of a hash function is basically impossible. It's not feasible, ideally. Okay. Given that the hash function is very secure, it's not very feasible to be able to brute force the hash value. Where they're trying to brute force the hash value basically. So as a result, that's the reason why a hash function is basically labeled as a one-way function. So remember, when you hash the data, the result basically might be typically smaller than the input, or ideally it should as we mentioned, it's always about fixed size. The output will always be fixed size. Okay. That's ideally with hashing. It doesn't matter if you have one sentence or message or an entire book. The result will always be of that particular fixed size, and this basically prevents an internal parties from figuring out how big or small the original input or message was. Okay, so kindly take out of that. It's a reason why whenever you're storing passwords in the database, you ideally have to hash them first. Okay, so for guys who are quite conversant with Web3 engineering, I think you very much about bcrypt, password hashing, and then PBDKF. Those particular algorithms for password encoding. This is basically what happens under the hood. Okay. I'm seeing there's a question from Will Cliff. So question, please. After hashing, does it mean that if a random person is given the hash, they cannot recover the plain? Yeah. Basically, you can't recover the plain text. You'd have to brute force it. So remember, hashing is not encryption. That's one thing to note. Hashing is not encryption. Yes, Kabiri will get a recording of his class. It's been recorded. Great. Is there another question on this before we proceed? So please, if you have any question, be free to text in the chat. So what are the properties of a good hash function? First of all, first property is determinism. Basically means that it will always give you an input, will give you an output of identical size regardless of the size of the input you started with. Basically, this means that if you're hashing a single sentence, the resulting output should be the same as when you hash an entire book, right? That's what we mean by determinism. Then you should have pre-image resistance. So to ideally know what you mean by pre-image, is that it's infeasible to reverse a hash value to recover the original input, the original plain text that you had. So basically, that's what we mean by a pre-image. Okay. And so sometimes you may see some other people talking about second pre-image resistance, basically meaning that it's infeasible to reverse a hash value to recover the original input plain text that you gave it. So what do you mean by can hash functions repeat? I think you may need to elaborate more on that, boys. Yeah, and so that's basically much about pre-image resistance. Like once you have the hash value, you cannot work backwards to get the original plain text. Okay, great. Then we have collision resistance. So what do you mean by collision is? let's say we have two words. Let's say we can have like hello and free. And a collision ideally will mean that when you hash hello separately and you hash free separately, they give you the same hash value. That's basically a collision. And daily is a good hash function should be able to be collision resistant. We wouldn't want someone to be able to we really wouldn't want someone to be able to be able to generate the same hash value for using a different piece of text, really. So okay, so it's basically computationally infeasible to find any two distinct inputs which hash to the same output. Okay, great. Then we have avalanche effects, meaning that any small change to the plain text that you're using, that you want to hash, ends up making the output to have such a very big change. So I think I can show this with an example here. We can have ideally SHA-256. You can just use a simple encoder. You see how this works. So I want you to see just how this basically works. So let's say we have a low. You can see this particular, as you can see how the hash value you have done there. Then let's say I add like a single character. What happens to it? You can't even tell that I added a single character. It's changed by such a very large value. That's what we basically mean by avalanche effect. A single change to the actual, the single change to the input results to such a drastic change in the output. Okay. And finally, we have the hash speed. The hash speed should basically be reasonable depending on the work you're doing. So as you'll be getting more familiar with hash functions, you'll learn that they define the speed they used in the hashing basically occurs. So let's say you are let's say like you're in the case of handling website connections. Ideally, you'd want the connection to be very fast, and you really want the hashing function that you're using for ensure the handling the website connection to be slow. So as a result, you might have to end up using a very fast website connection. But then let's say you come into password hashing. Okay, you want to make it very hard for someone to be able to brute force your password. So you have to choose a very slow hashing algorithm, and that's basically why I think the current standard for password hashing is bcrypt, because bcrypt is very slow. Okay, Steve and Carlos Kishana, please mute. Thank you. Yeah, so that's pretty much about hashing function. That's basically about properties of a good hash function. Okay. So down there's a link that it's basically a link to a paper that basically goes a bit more in depth into cryptographic hash functions, and ideally talks more about what we've been talking about here: the pre-image resistance, second pre-image resistance, and collision resistance. So it's all compulsive for you to read, but it's a very good read. It can help you very much understand all these concepts we'll be talking about here. It's very good as a web. Remember, yesterday as we were introducing the basics, that it's very good for you as a web engineer to be able to understand the kind of algorithms you're using. Could be any algorithm, like what's your blockchain network is using, or even the cryptographic algorithms you're about to use. So please make sure to go through that particular paper right there. Is hash speed in terms of time? Yes, it is. It is, Steve. Hash speed is in terms of time. Okay. Benefits of hash functions. So why do we use hash functions? They ensure data integrity. So ideally, since again, as we said, it's very hard to work backwards. It's a one-way function. If there's any change in ideally what you've hashed, we'd be able to know very, very easily. Yeah, because of the nature of hash functions, they're very secure against unauthorized modifications. And as we've already mentioned, we can use them to protect stored passwords. Okay. Perfect. Then yeah. So I think good examples of hash functions is like the message digest class of functions. There's the MD5. Then you have the secure hashing algorithms like SHA-1, SHA-256, SHA-512. And it's also good to note that algorithms like the MD5 they are rendered insecure. So if you do happen to work on something that where security is a very, very big aspect of what you're working on, please be sure to understand please be sure to understand whether the hashing algorithm you're using is secure enough or it's fast enough for that particular piece of work, or basically it has a reasonable speed for your piece of work. And that's much on hash functions. So
For what?
is there any question on this before we proceed to the next thing? Yes, Carlos, you'll get a recording of this class. Don't worry. Any questions on hash functions before we proceed to the next bit? Okay, so please feel free to ask questions. What is the meaning of SHA-1? So, ideally, the algorithms are basically they are named ideally after the designs they have. Okay. So SHA, but the baseline of the algorithm is called SHA. The SHA basically means secure hashing algorithm. And so basically that means that SHA-1 is really that was the first version of the secure hashing algorithm. Okay. And as time went by, they realized that the SHA-1 can be there's a way you can be able to sort of like so you can be able to let me use the word break the hash values of his algorithms. Okay. So they end up now basically you end up having iterations of this. So SHA-1 ideally should stand for SHA-1 with the 128-bit hashing. Then there's SHA-256 that handles 2056-bit hashing. Then there's also SHA-512 that should be handling 512-bit hashing. Okay, Samson, I hope that answers the question. What is the meaning of brute force? Brute force is basically it's sort of like trying to get someone. Really, what happens when you're trying to get someone's password? Okay, so let's say you're trying to access one of your friend's phone. What you will basically do, you will try all sorts. You will end up trying all sorts of combinations for a particular person's password till you end up finding the correct password. That's really what you're trying to mean by brute force. Okay. Wilson Osano Yeko, all Windows logins password hashes are stored at some file as MD5, meaning MD5 can also not be reversed. So again, depending on yeah, thank you for that, Arnold. So depending on remember what I mentioned, most of these hashing algorithms are not secure. Something like the MD5 algorithm, I believe should have been broken within the 1990s. That's why you end up finding a lot of people, a lot of applications don't use that particular. They don't use that. They don't use that. They don't use this. They don't use MD5 algorithm. But also, again, depending on how you use them, you can be able to sort of like add more secure add a bit more layers on top of MD5 to make it a bit more secure. That's why you find that Windows logins they might say they use MD5, but you may end up finding that they don't rely fully on MD5. They have their own ways of bypassing MD5's limitations. So yeah, so remember, as you said that these functions are one way, it doesn't mean they can be broken. No, that's why we have it. That's why we always have improvements in these algorithms. Okay. So I remember MD5 is not as secure as you think. It can be reversed. Actually, most of these algorithms can be reversed. They're not as secure as you might hope. But always make sure that you're always using the latest version of the hashing algorithm. And always be sure to be in touch with ideally what's happening within the tech space, so you can be able to know whether your application is safe or not. All right. So not seeing any other question in the chat. If that's the case, I think we can proceed now to the next bit, which is symmetric cryptography. So symmetric cryptography is basically just symmetric cryptography is ideally what most of us use. It's basically a scheme where we have a single key to encrypt the data and also to decrypt it. Okay. So ideally in this case, a good example of key primitive with this particular design is advanced encryption standard. And also we have the data encryption standard. Okay. So that is basically symmetric cryptography. You can think of it as you have a password and you need to share a piece of information, let's say, with your neighbor. So what will happen is you'd give your neighbor that password and encrypt the data you want to share with your neighbor using the password. Then you send the ciphertext to your neighbor. Even if someone else was to intercept a message, as long as they don't have the shared key, they won't be able to decrypt it. Then once your neighbor has it, they cannot decrypt the message and can now see what they're trying to tell them. That is basically symmetric cryptography. We just have a single key that we share between the two parties who want to communicate. Between the parties that want to communicate. Yeah, that's really much on symmetric cryptography. So is there any questions on this? Questions on symmetric cryptography? So please ask any question. If you feel like there's something that you still haven't understood, please feel free to ask. Please feel free to ask. Okay. So this same thing under symmetric cryptography, we can talk about ciphers. So I think one of the common ciphers you'll meet as a engineer, Web3 engineer, is Steve, really the difference between the two is basically in how they are designed. Okay. Well, AES and DES. I really wouldn't want to go in depth into ideally how they are designed because it can get a bit more technical. But what I'll do is I'll be able to share more data on this. Actually, I have also a lightweight implementation of the advanced encryption standard, so I can be able to share. I can be able to share that particular repository with you, so you can also check out if you want to look more into how these standards really work. Basically how you can build one if you want to. Okay. So just remind me, I can share the repository with you. I can also share some sources with you to ideally read more on this. But I really wouldn't want to go into the depth. It can take a lot of time we can take a lot of time to discuss this, and time is not really on our side. Okay. So is there sources to make more research and findings? Yes. So the slides have resources you can use to learn more of this. So when I share the slides, you'll have everything you need for that. What if an attacker gets the key from one end? Then basically they are able now to decrypt. They're basically that renders the communication insecure. So you can right off the bat you can see the limitations of symmetric cryptography. So if you're using this kind of a scheme, you have to make sure that the shared key is stored securely at all times. Okay. Okay, great. That's a very good question. Now, a stream cipher. So stream cipher really are the encryption techniques that work byte by byte to transform plain text into code that's unreadable to anyone without the proper key. So ideally, as you can see, the same key that really encrypts the message is also the same key that you can use to decrypt the message. But issue with this is that these particular ciphers have been broken already, and that's why I think once you'll be doing this kind of once you'll be starting a development, you realize that rarely will you find this. We rarely will end up encountering stream ciphers in a development course, they're not ideally safe. As you can see here, there's already like algorithms out there that you can use to ideally reverse encryptions done by stream ciphers. So as much as you can, please stay away from stream ciphers. Okay. So there's a link there that from stackexchange.com that talks about this more in depth. So please, when you be checking the slides, can you go read deep on this thing, on this. Then block ciphers is another type of cipher encryption that our cipher algorithm have. So block ciphers, these are encryption algorithms that break up text to they basically, what happens is you take a text, it basically takes the plain text, it builds it basically what happens is it creates blocks. It creates blocks of information, blocks of bytes with this particular plain text, and it ends up encrypting it. And there's a way it sort of like encrypts the blocks and then ideally concatenates them into like a single output of a fixed length in that kind of sense. And when we'll be reading more in depth into this, you'll realize that, especially for advanced encryption standard, you'll find these two particular modes right here that I've mentioned right there, that I've told you to read on: electronic code book and cipher blockchaining. So when we'll be dealing with advanced encryption standard, that is the AES encryption standard, you'll be finding these two modes a lot, and it's very good to understand ideally what they basically mean, and ideally what happens under the hood. So I think that the GitHub repository will share, it should be an implementation of AES with the electronic codebook mode. So all these things are on the book. All these things are on the slides that will share. So don't worry, when I share the slides, you'll find everything right there. Okay, take a Christian. Great. So yeah, so a good thing to also notice is that block ciphers are much slower than stream ciphers, and also because of how they basically behave. Block ciphers have this particular characteristic called where you see people mentioning about them, that they say that block ciphers have this thing called high diffusion. So ideally what they mean by high diffusion is that information from one plain text symbol is spread into several ciphertext symbols. So you find that when you sort of like transform one block and then transform another one, the results that you get from the plain text is widely different and widely differed from ideally what you got from the plain text. So it becomes quite difficult to even insert symbols without being able to detect ideally without being able to detect this particular this particular change in the data. Okay, because of how they are designed. So you might find that using block ciphers are actually very, very secure for this particular piece. So please also, when you get the notes, kindly read on these two particular modes, the electronic codebook and the cipher blockchain. They'll be really helpful, especially when you're dealing with smart contracts. Okay, or even just working on securing your keys on your application. Right. Okay, so is there any questions so far when it comes to symmetric key cryptography? Any questions?
Hi, everyone. I'm so sorry, Victor, for interrupting. Can you please mute your mic from your end? I don't know what happened, but the host is with AGK right now. AGK Agbo, if you're hearing me, you can just please make me the host. But please, can you just mute your mic from your end? Thank you.
Okay. So if there's no question, I think we can take a 5-minute break. You can just stand up, stretch a bit. I know this is a bit more of it's a lot. It may be a lot to take in at first, so kindly just take a break a bit, take time to digest what we talked about. Then I think we can now pick up on the next item. We can just take a 5-minute break, please. Then, but if you have any question, please feel free to ask in the chat. The Christian, please mute.
Hello, I suggest the host to mute everyone so that we can reduce the distractions.
Yes, I need the host to mute, but the host is not even replying right now. Like, I don't know what happened, but the host got moved. Okay, he has made me the host. Thank you. I'll mute everyone now. Thank you very much. So sorry about the interruptions.
Okay, right. What happens if you want to share an encryption message with more than one person? In symmetric cryptography, they'll have to have the shared key. So remember that particular key is very vital. If you don't have the key, there's no way you can. If you don't have the key and the algorithm is very secure, there's no way you can basically be able to extract the plain text. So these keys are very, very vital. It's the same case where, as we'll be looking in the asymmetric key cryptography in the next slides, where you had these cases where people with these people, the people who joined Bitcoin way early when it started, and they ended up losing their keys. They were never able to recover their wallets since they didn't have the keys. And once that is lost, it's basically lost forever. So and let's say if you had like, let's say you just had even like just one Bitcoin lying in your wallet, and if you lose the keys, that's basically it. You won't be able to get that one Bitcoin. Well, till someone is able to break the security within that particular network, which is technically it is impossible. So yeah, so the shared keys are very important. If at all you want to be able to extract value from the encryption text, you need the shared key. Okay, thank you, Mark, for that question. Any other question? So please feel free to ask. We still within our break. What if everyone loses the keys? Then that's it. Then that's it. There's nothing you can do about it. If the keys are lost, that's it. You have to get a new pair of keys to be able now to be able to communicate again. Let's keep the question stream again. Let's keep the question stream again. I think we'll have to. So what do you mean blockchain cannot be hacked without the keys? No, we're not meaning that not be hacked. Like what I'm meaning is the keys are very vital for you to. Yeah, the keys are very vital. The keys are extremely vital. Okay, so for you to basically be able to have control over to have control over your tokens and everything, you basically need the keys for that. But ideally, for how the blockchain networks are designed, it's not very easy. You cannot basically hack them. The point of hacking a network is basically just trying to hack a use of the network itself. So, but trying to hack a network, really, the blockchain network is basically impossible. Not unless you render one of the algorithms you'll be looking at insecure, you can't hack them at the moment. My phone was stolen, and I forgot to write out the keys, lost wallet, and altcoin. Yeah, you can't really recover that. That's gone. And that's why basically told to whenever you're creating a wallet, you have to write them down. Okay, you have to write the seed phrase down so that you can be able to recover them later on. Or is it not possible to do a phrase recovery setup on a crypto wallet? Because as we'll be looking at in the few slides, the key is that they derive from basically the seed phrase. Okay, and so when you don't have the seed phrase, there's no way you can be able to there's no way we can be able to work backwards towards the seed phrase itself from let's say like a public key. Okay, remember, the public key is even though it's sort of like related with the private key, you cannot work backwards to like the private key. Okay, so we'll be looking at that in a few. Okay, so let's keep your questions streaming in. We think we have 1 more minute. We have 1 more minute. Okay, so which programming language is to create in this? Actually, any Turing complete language can be able to do this. Okay, any Turing complete language can be able to create these cryptographic keys for as long as they can be able to handle the required math for it. They can be able to handle this. So you can do it in PHP, you can do it in JavaScript. Of course, you can do it in HTML. You can do it in Java, Rust, Go. Yeah. So any programming language can do this. And also the scripting languages, some scripting languages. Yeah. What's the difference between a private key and a 12 key phrase? So I'll be looking at that in a few. So I hopefully be able to answer your question. So I think you can start. So asymmetric key cryptography. So another name for this, another time you'll be hearing about this is called public key cryptography. So if you've heard of public key cryptography, another name for it is asymmetric key cryptography. Unlike symmetric key cryptography, in this scheme, we have two keys. We have a private key and we have a public key, okay? So how they're related is, these two keys actually, they're related they're related mathematically, okay? So what happens is the private key basically derives the public key. So the private key basically derives the public key, or the public key can be derived from the private key, but you cannot derive the private key from the public key. That's one thing you have to note. And so as a result, instead of you sharing both keys between the parties that want to communicate, you only end up sharing the public key. So let's say we have party A and party B trying to communicate. Okay. Let's say you have party A and party B trying to communicate. So the sender and the receiver will basically, what they can do is they will be able to now share the public keys to both of them, but they remain with their own private key. And the idea behind this type of cryptography is that the public key is used to encrypt the data, but the private key is used to decrypt the data. Okay. So once you encrypt the data with the public key, you can only decrypt the data with the private key. Okay. So kindly take note of that. It's very key to understand that particular bit of information, because that's basically the underlying theory, theory behind public key cryptography. So please take note of that. It's really just how that basically that's how it ideally works. And so some of the common okay. I'm seeing the questions. Please can you come over this diagram again with real-time transactions? Well, so let me try this again. Let me find a better way to explain this. So now in asymmetric key cryptography, you have two keys, okay? You have two keys. Okay, we have two keys in asymmetric key cryptography. So one of the keys we have is called, we have the public key and the private key, right? You have the public key and the private key. And so the public key is basically, the public key encrypts the data, but the private key decrypts that particular data, okay? So one key encrypts, the other key decrypts. All right, can you take note of that? One key encrypts, the other key basically decrypts the data. And so ideally what happens is that ideally what happens is how is I can start from where they're derived from. So I think with what I can start with the basic, ideally most of you are very much aware of is when you're creating a crypto wallet, the first thing they give you is a seed phrase, okay? So you'll be looking into wallets before we finish the class, but the first thing they give is a seed phrase. And so the seed phrase is basically what the seed phrase does is it's basically used to ideally seed for us. It's ideally there to seed for us like values that we can be able to basically generate. But you can basically be able to generate a private key. Okay. So from the seed phrase, we can get the private key. Hope that's very clear. Seed phrase, we get the private key. Then now from the private key, we can now get the public key. Okay. So now the public key is now what you share with everyone else, but the private key is what you remain with. All right. So what the sender has done here is they received the public key from the receiver. So we can they receive the public key from the receiver. All right. And so what happens is if the sender wants to send a message to the receiver, the first thing they do is they will encrypt the data with the public key, with the receiver's public key. Then once the receiver gets the message, they decrypt the data with the private key. And that's basically how public key cryptography works. I hope that's a bit more clear. That's really just the baseline of it. Okay, one key encrypts, the other key decrypts. Okay, and so I think the algorithms that are very much used for this, the most popular ones you'll find is we have the RSC algorithms. I think you've seen. I know in your programming journeys, I believe you must have seen RSC from somewhere. Then we have elliptic curve cryptography, which we'll be looking at ideally just a bit more of them in our programming. I think together we'll be doing this. So yeah, so even in terms of the length, you realize that the keys are much different in terms of length too. Yeah, so I don't really want to go in depth into how this basically behave. But I think we can go to the next slide and ideally talk about how this ideally are the types and the classes of these particular algorithms. So the first family of asymmetric algorithms is integer factorization. So basically that means is we generate I think let me Max kindly mute. Yeah. Right. So integer factorization, really what happens is, at this point is we basically the generation is based on the large integers that are very hard to factor. Okay, that's basically the baseline of integer factorization. And the algorithm that uses this is RSA. Okay, RSA basically uses integer factorization. Now, the next one is discrete logarithm, where it's ideally where the generation is based on a modular, on the modular function. Okay, and so the result, basically the result of this is that it becomes quite, because of how it's designed, it becomes quite infeasible, computationally feasible to find the exponent of the generator. So basically this means that it becomes very difficult to find the input from the result. So again, remember, you don't really need to know the in-depth workings of these functions, but it's just good to know ideally how they just good to know where they come from, so that whenever you want to go learn more deeply about them, it becomes a bit easier to know where to start. Then we have the last one, the type family we have is called elliptic curves. Okay, So on the leafy curves, you have the ECDSA, and we have the leafy curve ECDH key exchange. Okay. So for the leafy curves, these are basically derived from the algebraic the cubic curve function. I think I can send it on the group, on the chat. That's I think that's not really. Let me just correct that a few. Plus x plus b. Yeah, that's more clear now. So that's really where we get the curve from. Okay. So now the keys are basically generated from points in that particular curve. Right. So again, remember, I don't expect you to know the in-depth workings of these particular algorithms, because these are not things you can learn within a day. They will take time to learn, but please, whenever you have time, make sure that you can. And really just make sure you can go, just sort of like have a slight overview of how these particular functions work, and just understand them, and just take time to understand them, really. Okay. So please, if you have any questions, kindly take time to ask. Right. But that's really much about asymmetric cryptography. Okay. So the major differences you need about this and symmetric keys. In symmetric key cryptography, we have one shared key. In asymmetric or public key cryptography, you have two keys. Okay. So in the symmetric cryptography, this one key is now used for encryption and decryption. But in asymmetric, one key is used to encrypt, the other is used to decrypt. Okay. And as we'll be looking at in the digital signature, that doesn't mean that when you encrypt the data with the public key, you can't decrypt with when you encrypt the data with the private key, you can't decrypt with the public key. No, you actually can, but that now goes against the design of these particular keys. So ideally for that is, as we'll be looking at in the next slides, it's that particular flow is used for something else, and it's very good for you to understand this particular difference right there. But now when you come into asymmetric, when you come into public key encryption, make sure that whenever you're encrypting your data, use a public key, and when you are decrypting the data, use a private key. Okay, that's really much about it. So is there any questions on asymmetric key cryptography before we move to the next section, digital signatures? Any questions? So Caleb, as I said, asymmetric key cryptography uses two keys. So in asymmetric, one key encrypts the data, and the other key will decrypt the data. So then another thing to note is that once you encrypt the data with one key, you can't use a particular key again to decrypt it, really, even with this particular type of cryptography. Okay, you can only decrypt it using the private key, using the other key. So okay, right, thank you for that, Samson. Okay, so but it's good to know, it's very good to note again, I'm going to mention this again, it's very good to note the public key is not only used for encryption. Okay, so that's why you find I'm really stressing on the one key bit. Okay, so you can use the public key or the private key to encrypt, but whichever you use, you have to use the other key to decrypt it. Okay, so if you use the public key to encrypt the data, you have to use the private key to decrypt it. If you use the private key to encrypt the data, you have to use the public key to decrypt it. Okay. Yeah. So yes, exactly. That's the right. Yeah, exactly. Great. So if there are no more questions on that, we can go to the digital signatures. So a digital signature, just from the looks of it, basically means it's basically a scheme of really being able to tell whether a message or document is authentic. Okay. So how is this basically calculated? You hash the value of that data, then you basically sign it with your private key. So now, in terms of terminologies, when you basically when you're really transforming the data using the public key, that is basically called encryption in asymmetric key cryptography. But when you're transforming the data using the private key, that's basically called signing. Okay. So can you take note of that? Right? I'm going to type it in the chat. So when using the public key, signing is when now you're transforming the data with the private key. Then encryption is now when you're transforming the data using the public key. Okay. And so ideally, why is this the case? You want a situation where if I basically generate some piece of data, you want to basically know that it is I who basically generated that piece of data, and ideally what is I is basically there is basically authentic without any tampering that has been done. Okay. So please okay, let me type this in the chat again. So transforming data with the public key. Data with the public key is ideally, that is we basically call this encryption. Then vice versa is signing. Okay. So then I think it's also good to note here if one key encrypts the data, only the other key can. Only the other key can decrypt that piece of data. Okay. Right. So can you take note of the differences? Huh? So you said signing is when you're using the private key to transform the data, and encryption is now when you're using the public key to encrypt the data. Right. So moving on to the next slide. So why do we basically need digital signatures? So the first bit is we need to prove authenticity of our message. Okay. So ideally, a digital signature can help us verify the message as a receiving party, that the message basically came from me. Let's say I'm the one sending a message to you. How can you basically tell it is me? It's by using basically using the digital signature. Why? It's because it's only I who has. Remember, when I was communicating with you, I only shared the public key with you. I have my private key. So what happens is I sign the data using the private key and I give it to you. And so since you have my public key, you can tell that you can be able to decrypt the data, and you can basically be sure that this really came from me. If it came from someone else's private key, you try decrypting the data using my public key, you basically will know that that's not my message, it's someone else's message. Okay. So as a result, digital signatures help us to prove authenticity, of the message. Now, they also help us to prove unforgeability of the message. Okay. Right. Thank you for that. We'll be getting to that. Okay. So they help us to prove unforgeability of the message. So only the sender of the message is able to use the signing functionality using the private key. Okay. So meaning that no one else can be able to produce a signed message that has been produced by really the person who signed the message itself. That's really what we mean by unforgeability. Like, since I'm the one who has a private key, no one else can be able to produce that particular message unless they have my private key. Then the last one is non-reusability. And that basically means that the digital signature cannot be separated from a message and used for another message again. Okay. So basically that means that a digital signature ideally is it behaves like a hash. Since a hash is unique, the digital signature is very much also unique. Okay. Right. So can you take note of that? And I believe this will really be a very good show of what we've been talking about. So as you can see on the left side, we have the signing of this particular piece of data. So we have the data in the hash function, which basically ideally hash the data we have there, then encrypt using a private key. We now generate the signature, and now we attach it to the data. We now attach the signature to our data. Okay. So now once the verifier now receives the data on their end, what they do is they will take the data and hash it themselves. Then they will take the signature, decrypt using the public key, and compare the hash values they have from both of them. Okay. So now at this point, you can really see the properties you can really see the properties of a digital signature and why we use them. You can see that you can only decrypt the data using the sender's public key that now proves authenticity. And you can very much tell that the data and what the data is basically it has not in any way been tampered really in any sort of way. Okay, so basically that is the idea behind digital signatures. Okay, so kindly make sure that you can understand what you're seeing on the screen, because this is very much needed in terms of as your life as a Web3 developer. Digital signatures will be your lifeblood as as you be getting into development. So please make sure you understand the difference between encryption and understand the difference between encryption, hashing, and digital signatures. Okay, Caleb. So on the left, what you have is signing. Okay, and then the right we have the verification process. Okay, so on the left side we have the signing bit, on the right side we have the verification process. So on the left side, what is happening is the process of encryption, creating a digital signature is we have a combination of both hashing and encryption. Okay, right? So I hope that is clear. You cannot call a digital signature as a collection of timestamps. You can't call that time. You can't call that. Yeah, you can't call them that. So now, what happens is, as you'll be looking at the next slide, for it to be a digital signature, hashing itself is not enough. Okay, hashing itself is it's never enough, because ideally it won't be a complete digital signature. So that's where now the private key basically comes in to prove that the message came from us. Ideally, like to prove that this basically particular piece of data is basically came from me. We need the encryption bit using the private key. Okay. So to get a digital signature, you first have to hash the data. It keeps the data using the private key, and now you have the signed. Now you have the thing. You are now attached the data. You basically now have the signature once you do the encryption. Okay, and so when someone now gets the signed data on the end, they really take the signature and decrypt the the signature using the public key. Then they now take the data and then hash the data, and now they'll have a hash. They'll have the hash of the entire data that we gave to them, and they can be able to compare whether those two particular hashes, what they got from the signature and what they got from the signed data from the data, basically if they match. Okay, that's really what is happening. Good stuff. Good stuff. So please, if you have any questions, kindly continue to type them in the chat. And so there are two approaches to creating digital signatures. So we have the first one, which is sign, then encrypt. Then the second one is encrypt, then sign. Okay. So in the first one, where we sign then encrypt, the sender digitally signs the data using the private key, and they append the signature to the data, and then they encrypt the data together with the signature using the receiver's using our private key. Okay. Using the receiver's public key. We've got this is more secure. It maintains integrity and authenticity of the message before encryption. Basically it also makes this is actually more resistant to attacks. So there's this very common attack for digital signatures called a chosen ciphertext attack, where it's you can find like where this is sort of attack where the attacker basically tries to manipulate the ciphertext so they can see whether they can get a valid signature on any random messages. Okay. So can you take note of that this is actually compared to the second one, this is actually more secure. Then the first method is preferable. Then in the second method, the sender first encrypts the data, and then they sign the data. Then after they encrypt the data, then they just send the then they basically just digitally sign the encrypted data afterwards. So what this basically is that it ends up exposing the signed ciphertext to manipulation of attacks, especially the signing key is exposed. And it also ends up raising a bit of non-repudiation concerns. Basically meaning that if a signature is applied after encryption, there might be difficulties in proving the origin of the message since the message has already been it's already been hidden. Like since the message is hidden, we can't tell exactly who sent it. Okay. So and a problem with this is that if I was the one who sent it, you can't tell whether it was I who sent it. I can be able to deny any responsibility on that particular piece of content. So as a result, it's always advisable that you first sign, then encrypt, okay? So you first sign, then encrypt before you send. Yes, the first one is the best. You can use both of them, but preferably the first one is best. Is the best to use, okay? The first one is the preferable one to use. Okay, so where are they used? They used in validating transactions in the blockchain, okay? Each transaction basically has a digital signature from the initiator's private key, okay? So ideally, once you have a transaction, you can be able to validate that transaction, and you can tell whether the transaction was tampered in any way, and it is really from the initiator. And if you can basically, ideally can be able to validate that, you know, that particular transaction is good to go. They're also using consensus mechanisms. Basically, like in proof of stake or proof of work, you find that the participants have to sign blocks or transactions to validate them, okay? Like example is proof of stake where the validators they have to sign the blocks first before they're able to validate them. And as a result, that's where I basically end up using digital signatures. And you can also use them, they're also used in smart contracts. So you ideally want to, let's say you're saving health data. It's trying to save some health data. How will you know a particular data was saved by a particular doctor, and that the data that is there of a particular patient, of a particular, let's say you're saving ideally historical data for a patient for a particular day. How will you know? How will you be able to tell that that piece of information that you have is basically valid? It's from the doctor themselves, and nothing about that patent has been tampered with. That will be basically a digital signature for that. So signatures can also ensure that only authorized participants can trigger certain functions or changes within the smart contract. And that's ideally where we use that's basically where we use digital signatures in the blockchain. Okay. So yeah, that's ideally much about digital signatures. So please, if you have any questions, feel free to ask. Okay, just feel free to ask in the chat. And yeah, so don't know, is there any questions before we proceed? Any questions? Any questions? Any questions? All right. So well, if there's no question, I guess if that's the case, then I'll be asking questions. And then, oh, I've seen there's a question. The way the transaction validation well built in these smart contracts. Not really. This is already handled by the network. You don't really need to validate the transactions in the end. Ideally, what you can just do is just make sure that the rules of whoever is calling the contract, ideally, whoever the person is called the contract, following the rules of set in the contract. But the transaction validation is done by the network itself. It's not done by you. Okay. So that smart contract basically just adds more functionality to the network itself, depending on what you're trying to do. Okay. So any other questions? So please feel free to ask, or I'll be asking questions at the end of the class. So ask. Okay, so if there's no other question, we can now proceed to the last bit, which is digital signatures are used when. Yes, they are color. Okay. We can proceed now. The last bit we'll be looking at is wallets. Okay, we'll be looking at wallets. So remember, we say that the point of interaction with the blockchain are your keys. Okay. So well, blockchain networks use they use asymmetric cryptography. Okay. So meaning that when you're trying to communicate with the blockchain network, you need to have you need to generate private keys and public keys. And now from a public key, as you had said, actually just to ask a question, where do we get our public keys from? Let's say you have a private and public keys. Where do we get our private keys from? Where do you get our address from? Sorry. Where do we get our address from? I think we had mentioned this yesterday. Private keys, not exactly. Close, but not exactly. Where do we get our address from? Where do we get our address from? If you look at it, it's among the first slides in our yeah. So yeah, exactly. So ideally, our addresses are derived from their public keys. Okay. So of course, trying to store these keys can be quite a hassle. Okay. So what happens is we have softwares called wallets. Correct. We have softwares called wallets. So basically the wallets, the work is really just to store the private or public keys and addresses, and also yeah, thank you very much, Christian. And ideally also they assist us to be able to and like another functionality of wallets is they also are possible to transact with the network itself. So we have categories of wallets. We have 3 categories of wallets. We have hot wallets, cold wallets, and warm wallets. And it's paramount that you understand basically what you mean by hot wallet and cold wallet, or a warm wallet, as you get into Web3 engineering. So basically the wallets are ideally categorized depending on how they interact with the internet. Okay. So the first one is a hot wallet. So hot wallets ideally connect, they always connect to the internet. Okay. So ideally that means that the private keys are always that are used to send transactions are similarly online. Okay. And that means that the transactions can be created and recorded in the blockchain and in an automated way without the need for you having to having any involvement with that particular wallet, with it directly. But the issue with having hot wallets is that you have to notice that they can be more vulnerable to theft, especially if the security of your keys are compromised. Okay, that's basically what a hot wallet is. Then a cold wallet, ideally, the private keys are stored completely offline on a device that is not connected to the internet. So a good example would be hardware wallets. I think you must have seen wallets like Ledger, Trezor. Okay, those ones are now examples of hardware wallets. Ideally, now you need direct input. It needs direct input from you to use as well. If you ideally be able to sign transactions and yeah, to use them, to even access the keys. Then the last step, you have a warm wallets. So warm wallets are ideally the keys are held online and transactions can be created automatically. But for you to do this, you need involvement to do that. So ideally, the keys are not ideally online all the time. They're only online when they needed to be online. Okay, that's basically an example. That's basically what home wallets are. All right. So just on top of what we have here as category of wallets, we now have the actual types of wallets under them. Okay, so we have the first type of wallets we have are non-deterministic wallets. So basically this means that the wallets basically they randomly generate private keys. Okay. I think another name you might get for this kind of wallets is just a bunch of key wallets. Okay. So the keys that are generated are not in any way related to each other. Right. The keys are not in any way related to each other. So that basically means that managing a large number of keys is quite difficult and error prone, and basically, of course, can be error prone. It can lead to theft and loss of coins. Moreover, there's a need to create regular backups of the keys and protect them appropriately in order to prevent theft or loss. Okay, so MetaMask will fall under, yeah. So ideally, MetaMask, that's why you can also say MetaMask is it's a warm wallet because you need to basically approve a particular transaction for it to go through. So then the next type of wallets you have is deterministic wallets. Okay. So in this type of wallets, keys are derived out of a seed value via a hash function. Okay. So this is where the idea of a seed wallet basically comes from. Okay, the seed phrase basically comes from this place now. Once you have the seed phrase, you can basically be able to derive your keys at any point in time for as long as you have the seed phrase. Okay, and there's a particular standard that ideally manages this is the WEB3, which I've just basically mentioned that you have to go read. The WEB3 basically it also defines the mnemonic calls to be used. Okay. So the seed number is generated randomly and is commonly represented by human readable mnemonic code words. Okay. And so the phrase cannot be you can also use the phrase to basically recover your private keys in case you lose them. So that's ideally behind the deterministic wallets. But for as long as you have that means that for as long as you have that particular seed phrase, you can always get our keys. Then hierarchical deterministic wallets, ideally, the difference between these is that HD wallets or hierarchical deterministic wallets, they store keys in sort of like a tree structure. Okay. So what happens is the seed ideally it generates like a master key or what we call a parent key, and it can use this particular master key to generate other child what are called child keys, and which can also generate things of what we call grandchild keys. All right. And so what happens is that the idea behind these wallets is that the keys aren't ideally generated directly. They instead generate information as we're reading into those standards down there, what we call private key generation information. That's what is basically generated by this key, ideally generated by this phrase, which can now use to generate a sequence of private keys that we can now use for our transactions. And as a result, the complete hierarchy of private keys in HD wallet is easily recoverable for as long as you have the master private key. Okay. And it's also good to note that because of this property, it's very easy to maintain and these particular types of wallets. That's why you realize that a lot of wallets actually use HD wallets. Okay, they're actually HD wallets. Now, there's also number 4 brain wallets. Ideally just meaning where you memorize the passphrase, and the passphrase is now used to generate the private key. Okay, so you have your passphrase, you memorize it. Then you enter your private key. The private key is hashed and it's now used to generate a private. You enter their password. The password is hashed and we use it to generate a private key. Okay. Then there's a paper wallet where you basically write the keys on a the keys are put on a paper. Then we have hardware wallets, which ideally, example are like Ledger or Trezor, which ideally you keep the keys on a physical device. Then ideally, now we want to make a transaction, ideally have to connect the physical device to whichever machine you're using for that transaction. Then you have online wallets that ideally store they are entirely where the keys are stored entirely online, and they are provided as a service usually by cloud. Okay, so online wallets are yeah, that's basically a good example will be like crypto exchanges. Most of them actually just create for you the wallet, they create for you the wallet, but you never get access to your keys really easily. Like, but the exchange basically manages for you the whole thing. So it's really you just using the service to actually access the network and its services. Then you have mobile wallets. They're installed on mobile devices. Okay, so that's basically just a mobile wallet that's stored on your mobile device. And for the sake of understanding more of how these wallets work, kindly look into those two standards down there, BIP 39 and BIP 444. Okay. Great. So is there any questions when it comes to wallets? Any question when it comes to wallets? Any question when it comes to wallets? Okay. So there's no question. I think it's good to now mention what I require of you guys tomorrow. Please, what did you say about paper wallet is? Paper wallets are basically paper wallets ideally you just write the keys on a piece of paper. So you can have them printed on a piece of paper, or you just write it in there on a piece of paper. Then when you use it, you need when now we need to use a wallet, you really just get the piece of paper, really. Okay. Yeah, any other question? Any other question? Number 3 and number 4. Okay. So what would you like to know about number 3 and number 4? AGK. Just type it on the chat. Hardware wallets are no, not really. A hardware wallet it's a physical device. Okay. Let's say this is a good example. You see, this is this is what I mean by hardware wallet. You can see right here. Can you see this? This is not what you mean by hardware wallet. Right? Okay, that's basically a hardware wallet. Trust wallet. Trust wallet is a mobile wallet. You can see this is ledger. That's what we mean by a hardware wallet. So BIP 39. Actually, the Ethereum Foundation is actually has a very good documentation on this. There's a BIP 44. So you can just come into the wiki and you can look more into this. Okay. So you can just come and change the structure. And you can also find that information right there. Okay. Right. How are they sorted? Can one call a bound token hardware wallet? What do you mean by that? Bound token hardware wallet. Okay, so I think as the questions come in, we can look into what now expect of you today, tomorrow. So please make sure that once the form has been sent, kindly submit your assignments. Okay, just kindly submit your assignments so we can check them out. Then also be sure to share whatever you worked on. Be sure to share whatever you worked on with everyone else. Okay. So kindly just, if you have presentations, kindly just share them on the group so that everyone can see really what you're able to find. So let's share information within the community really. Okay, great. So which wallet is recommended for Web3 projects? Ideally, what happens is you are how are you sending them? The projects there's a Google form that's going to be shared with you. So once it's shared, kindly just submit it there. So what happens is for Web3 projects is that ideally what happens is people you generate the keys and you ideally store the keys somewhere securely. Okay. So the people use vaults. They use software vaults for that. There's a good one is like HashiCorp Vault where you can store your keys, and you can be able to now you can now be able to interact with the network really from the keys themselves. You can also use a wallet as a service applications for that too. So yeah. Great. So reading assignments, especially when you'll be getting to smart contracts, it's very good that you understand the idea behind or you get to understand what is a multi-sig, and get to understand what is multi-party computation. Okay. Then right there's a very good article on how we generate wallet addresses from private keys. So as you remember, as you mentioned that we get public keys we get addresses from the public key. It's very good to understand how we do this. So because of time, we may not be able to go through this, but please kindly make sure that you go through that. I will be asking questions on that. So to get ready for tomorrow's class, that will be the first practical class. Kindly set up, make sure that you have Node.js set up locally on your computer, and any text editor really. You can have Visual Studio Code, you can have Atom, whatever you very much comfortable with. Kindly install that. And also be sure to just check out Hard Hat, this particular website right here. So you just go to the website. They don't really need you to do anything. Just go check it out. Make sure that you're very much acquainted with ideally what you'll be seeing here. Make sure you can just go through it really. Make sure you're very familiar with it so that during tomorrow's class, as we now get into the practical bit of things, you're able to ideally catch up very easily. Okay. But that's ideally an introduction to the cryptography. There's so much that we've not done that we may need to go through by yourselves. But I hope that but whatever is here in the slides is basically enough for you to get started. Okay. So remember, it's a process of learning, it's a process of growing. You have to read and read more until you get very comfortable with them. Okay. So that's much about today's class. So yeah, I don't know, possibly you can just type in the chat how you feel about today's class. I know it's been a mouthful. I know it's quite been a mouthful this, but yeah. Please feel free to ask questions even in the group, in the WhatsApp group. Please feel free to ask questions. So yeah, so how do you feel? How do you define this class? Just type in the chat. How do you define this class? Quite informative. Okay, good. Yeah. Right. Yeah. Yeah, the slides will be shared with everyone. Don't worry. Slides will be shared with everyone. Everyone will have the slides with them. All right. It was encrypted. It's very funny. Yeah. But I assure you that today's class was basically the hardest. The other ones are very easy, so don't worry. The other ones are very easy. So please guys, make sure that I know you worked very much. I know you worked on the Santip here. I know you worked on the I know a lot of you created slides for yesterday's assignments. So even as you share them, submit them on a Google form, please make sure please make sure that you can please make sure that you share them with the group, okay? So at least we can see what you came up with. We're all learning really. So really make sure you share the group with everyone. Great. So without much ado, I think that's much of today's class. That is Introduction to Cryptography. And hopefully as time goes by, we can be able to learn more deeply from each other in this concept. So yeah, Aisha, I think we're done. Yeah.
Yeah, thank you very much, Victor. This class was very, very insightful, and I'm sure attendees learned a whole lot, right? Talking about cryptography, talking about encryption, talking about decryption, and all of that. So, guys, thank you for attending day 2 of the Blockchain Basics for Web3 Developer. Do make sure you share your journey on social media and tag Memoy Africa on all platforms. LinkedIn, Twitter, Instagram, anywhere you're sharing. And please, let's just make sure we read on the assignment that Mr. Victor has shared with us. So I'll see you guys tomorrow, same time, same place. Do have a nice day. Bye, everyone.